So folks, we're now going to step up this summation notation by another level, and this makes it a little bit harder. The first thing to keep in mind, and I guess I didn't make a spot for this, but let's go ahead and make, here we have the x-axis, say, and then let's say we're partitioning it between this, here we have A, and here we have B. So we always enumerate this as our x naught. And then I want you to think about stepping, if we're going to do this, and in this case we're assuming we're at equal width, I want you to think about stepping one interval to the right. So this would be A plus delta x for that entry right there. Likewise, this entry right here, you could label it many different ways, but one way to label it is A plus 2 copies of delta x, because delta x is supposed to be the widths of these intervals. So each one of these intervals has width delta x. So you could think of saying one way to obtain this element in the partition is to go to A and then add to it 2 copies of your delta x, and you'll arrive there. Likewise, and I'm running out of room to label this, but this would be A plus 3 copies of delta x, etc. For this very last interval, this would be right here. This part's a little bit hard to enumerate. This would be A plus n copies of delta x if I'm breaking this up into n intervals. So I want you to spend a moment to think about why that's the case. Why would I call this element in the partition A plus 1 copy of delta x, and this element in the partition A plus 2 copies of delta x? So that now enables me to give a more general Riemann sum, and I'm going to start off with the left Riemann sum. So always we're using this to approximate the area beneath the curve, and here I'm just going to write else of n because I'm not specifying how many rectangles I'm using in this problem. But we are going to assume, at least for the first collection of these, that we have equal width. So if that's the case, I'm going to think about adding up the areas of a bunch of rectangles. Folks, I'm going to scoot this over some. So I want to think about adding up. So there's our adding up. This is a height times a width. So this whole thing here is an area. We're going to be adding up the areas of a bunch of rectangles. We've said that in this class we will always start our counter at k equals 1, and we'll stop when we get to n. That's because we're going to call this first interval right here, that'll be the base that we use for our first rectangle, and this base here will be the base that we use for our second rectangle. So see how we're counting it. This is 1, 2, 3. So that's why I start my counter and I stop at n. And in fact, let's just make sure we get this part down here. For our right endpoint method, it's going to look very similar. It's going to be r sub n, and it's again going to be the sum from k equals 1 to n of f of, and then delta x. But the hard part is, what do we decide to place here? And what I'd like to do is, unlike one of our earlier examples, where we enumerated by the number of the element in the partition, so we had x of 0, or x of 1, or x of 2, and then we had to go look up, well, okay, what did we call x of 1? It was 6. Or what did we call x of 2? It was 10. I'd like to construct a Riemann sum that does all of that process automatically. And so what we're going to use is, for our left endpoint method, we're going to use a plus, I still need a little more room, a plus k minus 1 delta x. I want you to see how that works. When my counter is 1, I'm going to do a plus 0 copies of delta x. If we go look at this generic interval here, when I'm doing my left endpoint method, here would be, I'm going to put it in purple here, here would be my first interval. And if I'm doing the left endpoint method, what element from this first interval do I want to plug into my function? And the answer is the left endpoint. Notice I'm referring to that as a plus 1 minus 1 times delta x. But 1 minus 1 is 0, So we get 0 copies of delta x. So for my left endpoint method, it'll just be plugging a into the function. Contrast that with what we're going to do for the right endpoint method. This is going to be just a plus k delta x. And what I'd like you to do is convince yourself when I do this for this first rectangle here, I'm going to be using this interval, and I want to use the right endpoint of this first interval. So how could I systematically get there based on my counter k? I'm going to start at a and step over 1 copy of delta x to get to what I'm going to plug into this function. So let's do one more. Hopefully this will help to clarify it. Folks, this is very challenging, so if you're struggling with this, please don't beat yourself up. This is a tough topic. Okay? So for my second interval here, if I were doing the left endpoint method, I want to make sure I take a plus delta x. Notice that for my second interval, my counter would be at 2, and if I plug 2 minus 1, I get 1 copy of delta x plus a, and that's precisely how I'm labeling that left interval. If I want to do the right endpoint method, then I'm going to want this element right here for my second interval. So if I'm on my second interval, that's for when k is equal to 2, and notice that this would be a plus 2 copies of delta x. That is, start at a, go over 1 copy, 2 copies, that grabs that right endpoint of that second interval, and that's what we'll be plugging into the function to figure out the height. Notice always we've had these delta x's, which stand for the widths. Now this becomes a little bit confusing here, folks. How come? Because here I have a delta x that's sitting inside the argument of the function. Okay? So I'm going to remove this for just a second here because I want to convince you that we're just doing what we've always been doing. Oops, that didn't quite work. So there, I've removed the argument that was inside this function here. I've removed it. And you can see that we have what we've always had, where we're taking something and plugging into the function. That gives us the height of the rectangle, then multiplying by the width. It's just that when I think about how to decide what number to plug into the function, I need to use an expression that involves copies of this delta x, because that's how I think of stepping from my initial value over to the other values in my intervals. So I've colorized this. Hopefully that helps you see that's what's going into the argument of the function there. But it's the same height times width that we've always done. This delta x, though, is what enables me to step to the subsequent elements in my partition. Okay, so folks, you need to know these, and my recommendation is you spend a little bit of time trying to get familiar with why I chose that for the left endpoint method and why I chose that argument for the right endpoint method. But at the end of the day, you just need to have those two memorized. Okay? Now, in a moment here, let's go ahead and do it now. I'll give you the same thing for the midpoint method. For my midpoint method, the most useful way to write a Riemann sum, as long as we have, again, this assumes equal intervals, will be the sum from k equals 1 to n of f of, let me go just even a little further there, f of some expression times delta x. Now what's a little bit harder here is when I go to do my midpoint method, I'm going to put kind of a more complicated looking formula in here. I'm going to put in the formula 2k minus 1 over 2 delta x. So that's the formula that I'm going to use that helps me step to all of the various midpoints of each of these abstract intervals. That's going to take me to that point and that point and that point for each one of the intervals that I want. I'll convince you why that's so right now. So how did we get this formula? What we did was we thought of averaging this endpoint and this endpoint of the kth interval. So if I were to add those two together, a plus k minus 1 delta x, that's the first term. I'm going to add to that the second term, a plus k delta x, and then I'm going to divide that by 2. That's always what we've done to find the midpoint of two values. For example, if my two intervals, let's say this was at 20 and at 25, how would I find the midpoints of those two? I would add 20 to 25 and divide by 2. So that's what I'm doing for the arbitrary kth interval. I'm adding its left endpoint, which is this, to its right endpoint right here, and then dividing by 2. And so if we do so, in the numerator I'd have 2 a's added together. I'd also have 2 copies of k delta x added together, and I would have a minus 1 delta x all divided by 2. There's lots of ways I could then write this. What I'll do is I'll go ahead and divide the 2 into the first term and into the second 2 terms. So that gives me 2a over 2 plus 2k delta, and then in the numerator I'm going to factor out that delta x. So 2k minus 1 delta x over 2. So this is not too bad, folks. I went ahead and divided the denominator to the first term. That's where I got that from. And then I went ahead and from these second 2 terms, the second and the last, I factored out the delta x. That left me with 2k minus 1. And then I divided 2 into that. So then this gives me just a plus 2k minus 1 over 2 delta x, which is what I've written here for that midpoint method. That one is definitely a little bit harder to come up with, folks, and my recommendation would be and you're not going to have all that many midpoint problems, but my recommendation would be just to memorize that. Okay? Now, all of the methods that I've done so far, hang on there, folks, all of the methods that I've done so far have assumed we've used a particular way of selecting the x-coordinate that we're going to plug into the function for whatever subinterval that we're working with. Okay? But there's nothing that says, say we look at this purple interval here, which was our first interval, there's nothing that says I have to use my left endpoint method, or that I have to use my right endpoint method, or that I have to use my midpoint method. I could have picked any value from within here, and I would just call it x star. Okay? Now, because I'm going to have several of these, I want to say that it came for the first subinterval, so I'll call it x of 1 star. And then over here, maybe I pick this as the representative point that I want to plug into the function, and I'll call it x2 star. So the star just means that I'm not specifying whether I'm using the right endpoint method, the left endpoint method, or the midpoint method, or any method at all. I'm just taking some value from within the second interval. So the star sort of informs the reader that we're not choosing a particular method. So if I want to give the Riemann sum more abstractly, what I could do is to say that the area is approximated, and that should be an approximation there, folks. The area is approximated. The area is approximated by the Riemann sum. And notice I didn't call this the right Riemann sum or the left Riemann sum or the midpoint Riemann sum, because I'm not selecting a particular method for choosing how I pick these x coordinates. It's going to be the sum from k equals 1 to n of f of something delta x. Notice this is the same thing that it's always been. Okay? But here what we'll do is we'll go ahead and say that we're just going to take some x coordinate, and how do I say it's just some, not a particular one, I put the star on it, from the kth subinterval. So this is how we give the most generic form of the Riemann sum. Here we're still assuming that the intervals have equal width. Now, what if our intervals do not have equal width? So maybe this is my x number line here, and maybe my intervals, we're going to have this first interval, it'll look like this. The second interval, maybe it looks like this. The third interval, maybe it looks like so, etc. We have all of these different subintervals, and they all have different widths. Well, I would call this first one delta x1, and I would call this second subinterval delta x2, and I would call this third one delta x3 when referring to their widths. So notice I'm enumerating them by whichever interval we're referring to. So here's my first interval. It has a particular width. We'll just call that width delta x1. My second interval has a particular width. We'll just call it delta x2. And more abstractly, if we were way out here, maybe we'd call this delta x sub k for the width of the kth interval. So for that reason, folks, if we want to be even more general with our Riemann sum, and this is as general as we're going to get, we're going to say that the area underneath the curve can be approximated by a Riemann sum from k equals 1 to n of f of, and then I want to have a delta x, but when I use just delta x, that's assuming all the intervals have equal width. But in this way of partitioning I set, I did not assume that we all had equal widths. So I'll just call it delta x of k. Delta x of k refers to the width of the kth interval. So when my counter is 1, this would be delta x of 1, and it would be the width of this red interval here. And when my counter is 2, this would be delta x of 2, and so it would be the width of this yellow interval here. Okay. And so what am I going to plug into the function? Again, I'm not going to specify, maybe for this first one, maybe there's my x1 star. And for the second one, maybe there's my x2 star. And maybe for the third one, maybe I actually pick the right endpoint method, but there's my x3 star. So notice I'm not saying I'm using the left or right or midpoint methods, so I'm just going to call these entries the xk stars that I use for the representative heights of the functions. Okay, so I know that this has gotten fairly complicated over the course of these 3 videos, but this is as complicated as it gets for you as far as doing these Riemann sum notations. This last one that I've given you is the most abstract way of writing a Riemann sum, where I don't assume that all the intervals have common widths, so I don't write delta x, I write delta x of k. And I also don't assume that I'm using the left or right or midpoint methods, so I use x of k star. What you need to know, though, is if we're doing the left endpoint method, the right endpoint method, or the midpoint method, we also have these systematic ways of ensuring that we go through and select the right elements of the partitions. Now you might be asking yourself, why don't we just keep doing it the way we did here, where you just had these enumerated values? And the answer is, although this gives you a nice expression, it doesn't actually give you something that you could program a computer to do or a calculator to do if you were going to add up not rectangles from 1 to 5, but the areas of rectangles from 1 to 1,000 or 1 to 50,000 or something like that. And so that's why we need these 3 formulations for my left, right, and midpoint methods respectively. Okay, I'll see you in the next video, folks, for the last problem.